Today's topic is about waves. Actually, this waves chapter I will divide it into three parts. So, in the first part, we will be discussing about what are waves, and particularly we will confine ourselves to mechanical waves, the nature of waves, the speed of mechanical waves in elastic medium, and we will discuss in the second session about the formation, reflection of waves and formation of standing waves, and we will derive equations for the frequencies of different modes of vibrations of stretched strings and resonating ear columns. And in the third session, we will discuss about beats and Doppler effect. Okay, so now we will start with the preliminary concepts regarding the waves. A wave is a disturbance, actually, the mode by which energy or disturbance propagates in a medium. All waves need not require a medium for propagation. For example, light waves which we are receiving from the sun and stars require no medium for propagation. And we know that the space is empty. Large space between the earth and the sun or stars is almost empty. Therefore, even without medium also, energy can be propagated. Such waves are termed as electromagnetic waves, so which we will discuss in later chapters. But waves such as sound waves or vibrations produced in strings or in air columns, these are known as mechanical waves. And these mechanical waves require an elastic medium. So a medium having elastic properties and inertial properties. Without these properties, mechanical waves cannot be propagated. Now, waves are classified into two types. So, one is longitudinal waves and the other type is transverse. So this classification is based on how the medium elements or the particles vibrate with respect to the propagation of the wave. So if the particles of the medium vibrate parallel to the direction of propagation of wave, such waves are called as longitudinal waves. So the example for longitudinal waves are nothing but sound waves. So when I make sound, I will be exerting pressure on the air layers, and these air layers transfer momentum to the molecules in the other layers. So like this, the momentum of molecules from one layer to another layer will be transmitted. So therefore, what happens? Compressions and rarefactions are generated in the air or in the gases. So in the form of set of compressions and rarefactions, the energy propagates. So you can show like this. So let us suppose this is a compression and rarefaction, compression, and so on like this. So here actually the matter in bulk will not move, but through small oscillations the particles transfer their momentum to the nearby particles. Likewise, the whole layers will be transferring the energy to the next layers. So due to this, you will be observing certain regions in the air as compressed regions, certain regions are rarefied. So after transferring the energy to the next layers, these layers again come back. So that means again rarefaction will be observed. So in the form of sets of compressions and rarefactions, the disturbance propagates. So the oscillations of the particles in the air or gas is parallel to the direction of propagation of the wave. So this type of waves are known as longitudinal waves. And when we come to this transverse waves, here if the particles of the medium vibrate perpendicular to the direction of propagation, just as in case of waves generated on the surface of water. So when you observe, you will see crests and troughs. Similarly, the waves that are generated in stretched strings, or in the case of a stretched rope, let us imagine a rope is fixed at one end and at the other end is free. You move that free end up and down. You will see how the transverse waves are generated and then propagated through that rope. So here the particles will be vibrating perpendicular to the direction of propagation of the wave. So this happens because of a property known as rigidity property. So only we can produce such type of transverse waves in solids and with a little difficulty in liquids, but it is not possible to produce transverse waves in gases because their rigidity, they don't have this shearing, they undergo shear. That is, the shearing will be very large in case of fluids because they don't have definite shape. Therefore, when you apply a shearing force or shearing stress is applied, then what happens? Their shearing will be very large. That means they start flowing. Therefore, such fluids which cannot withstand shear, we cannot produce transverse waves in such type of media. Then, in strings, you can easily produce this transverse waves. So, examples for transverse waves are electromagnetic waves. You will be already knowing about this. Light waves are electromagnetic waves in which the electric field and magnetic field vibrate, oscillate, those vectors oscillate perpendicular to the direction of propagation of the light wave. And similarly, the surface waves produced in water or a stretched string, if it is plucked at any point, vibrates. So these types of waves are known as transverse waves. Okay. So a wave which propagates in the forward direction and never returns back is known as a progressive wave. Progressive wave. Any progressive wave will have a definite velocity and moves away from the point of generation, and it will never come back again. Such progressive wave is mathematically expressed in terms of a periodic function. Why periodic? Means the particles of the medium, while they execute periodic motion. So we use a sine function or cosine function to represent mathematically the displacement of the wave. So for our convenience, we consider a transverse wave produced on a string. So let us represent it like this. So it is a function of position of the element of the medium and instant of time t. So this can be written as a sine kx minus omega t plus phi. Actually, this is a combination of a linear combination of sine and cosine functions, and this is represented by this a constant called phase angle. So, because both sine functions and cosine functions are nothing but they are periodic, therefore, as a combination of these functions, we can represent a progressive wave in which the particles vibrate harmonically. And for the sake of mathematical purpose, we can write like this. This can also be written as some constant A sine kx minus omega t plus some constant cos kx minus omega t. And therefore, we can write this A, which we call it as amplitude. So I will explain later what is amplitude. So this is equal to a square root of a square plus b square, and the phase angle phi is given by tan inverse b by a. So, but of course, we are not much interested in this mathematical explanation, but we will confine to this equation in which we are going to consider the phase angle phi as 0 in the explanation which we are going to discuss now. We will talk about what are the characteristics of a progressive wave. So this equation represents the displacement of the particles of the medium as a function of its position and time. Here we may drop that phi, taking that initial phase angle. That phi is called as actually initial phase angle, and this can be taken as 0. By that, nothing will happen to the wave equation. So we can write this as a sine kx minus omega t. And one more point is, why we use this minus sign, and what happens if the symbol minus is replaced by plus. Here, this minus sign indicates a wave propagating along positive x direction. That means for the wave shape to remain constant, it should not change with the time or position. So for the wave shape to remain constant, the argument of the function must be constant. Therefore, as the time increases, the distance of the point under consideration also must increase. Then only this argument part will be constant. Hence, this equation represents a progressive wave, a wave moving in the positive x direction. Similarly, if you use the plus sign, that is kx plus omega t in the argument, it shows that the wave is coming towards the origin. That is, with increase in time, this x value should decrease. Therefore, this argument part remains constant. Therefore, a progressive wave moving in positive x direction is represented by a sin x minus omega t. A wave coming towards the origin is represented by kx plus omega t. Okay. So, let us come to this equation. Now, here, what is this A? A is called as amplitude of the wave. This is the maximum displacement of the particles or the elements of the medium when the wave is propagating. So, in case of, let us suppose let us consider a transverse wave for our understanding. Let us consider this a transverse wave, in which you see this is the maximum displacement. It may be in the positive direction, or it may be in the negative direction, or that is the downward direction. We consider this wave always to be positive, and the quantity here of k is known as wave number or propagation constant. Okay, here we can show that this is equal to 2 pi by lambda. But here, what is lambda? Already you may have some idea about this. Lambda is nothing but the wavelength. So, how do we define this wavelength means? Let us consider 2 points in the wave propagation which are in same phase. So, the distance between 2 points, successive points which are in the same phase, may be considered as wavelength. That is, by time, the particles of the medium make one complete oscillation. By how much distance the wave propagates, that is considered as lambda. So here we are showing this transverse wave. The distance between two successive crests or the distance between two successive troughs may also be considered as wavelengths. And here K is known as the propagation constant. Similarly, angular frequency that is omega in the expression is known as angular frequency. So already you got this term in first year oscillations, and you know angular frequency is related to the period of oscillation like this. That is omega is equal to 2 pi by t. So this expression already known to you, and where t stands for time period. That is time taken by the particles of the medium to make one complete oscillation. And this quantity 1 by t, it is nothing but number of waves produced in 1 second. So which we call it as frequency. And already we have shown that the relation between angular frequency and the actual frequency is this. Omega is equal to 2 pi mu. So this amplitude is the maximum displacement of the particles of the medium when the wave is propagating. Wave number K in the expression is known as the wave number or propagation constant. Of course, the same term we used in elasticity, that is spring constant, but that is different. This is different here. Though the symbols are same, here it is different. K is called as propagation constant, 2 pi by lambda. Okay, you can see the derivation in the textbook. Because the time is very much limited, I am not going to explain how this relation is obtained. Similarly, angular frequency, this already studied in simple harmonic motion or in oscillations in first year. And this reciprocal of the time period, time taken for one oscillation, which is known as time period, and reciprocal of that will give you the number of waves produced or number of oscillations in 1 second, which we call it as frequency. Okay, that is about the equation by which we represent a progressive wave. Then we come to the speed of a progressive wave. How do you derive the equation or expressions for the wave speed in a medium? Actually, the speed of a wave in a medium depends upon the nature of the medium. So, it depends upon its elastic properties and inertial properties. But we will try to show you the relation between the wave velocity, frequency and wavelength. So like this. Let us suppose a wave initially is like this. After some time, it has moved to some other position. And consider a point on the crest. So the displacement of this point, let us say x, has moved from here to here, and let that be delta x. The time interval is say some delta t. But the wave shape should be retained. Therefore, the argument part of the expression or equation x minus omega t must be constant. That should not change as the wave propagates through the medium. Therefore, I can write like this. So this is equal to k into x plus delta x minus omega into t plus delta t. So therefore, finally what we get is k into delta x is equal to omega into delta t. Therefore, delta x by delta t is equal to omega by k. So here in the limiting condition we can rewrite this equation like this: dx by dt is equal to omega by k. So this is nothing but rate of change of displacement. So that is nothing but wave velocity. So that is the rate of displacement or change in position of the wave from x to say some delta x, as x plus delta x. So there is a displacement of the position of the wave. So the rate at which the displacement changes is known as velocity. Therefore, the wave velocity is given by omega by k. But already we know omega is written as 2 pi times the frequency and k is 2 pi by lambda. Therefore, that 2 pi gets cancelled and finally the wave velocity is given by nu lambda. That lambda term goes to the numerator. So, in that way, we can derive the relation between wave velocity, frequency and wavelength. But here, this is a general expression applicable to all types of waves. Now, when we talk about the mechanical waves, whose wave velocity is independent of frequency and wavelength, but depends on the nature of the medium in which the wave is propagating. So, we will derive an expression with the help of dimensional analysis, because the actual derivation for speed of mechanical waves is derived by Newton, but we are not going to do that derivation here. Instead,